thank you for the introduction and thank you for having me here. I would like to thank the organizers for that. I am Deniz Genlik. I am a graduate student at Ohio State University, and this is my last year here. And I will be presenting some joint work with my advisor, Hsian-Hua Tseng. So this talk is based on these two preprints that archives numbers I put here. So let me start with the subject is about the Gromov-Witten theory, and let me start introducing the subject a little bit, and then go further. So in Gromov-Witten theory, sorry, why did I came here? I should go all the way back. You see screen now? I guess you see. Okay. So we have a target, and in this target, we want to count some curves meeting some algebraic subobjects. But we want to do this count in a way, instead of counting the curves directly, we want to count the curves by their parameterization up to some equivalence and some stability. We put some stability condition on this on the moduli space objects, these objects, and these are called moduli space of stable maps. I have seen this drawing in one of the talks of Okonko when I wanted to put some animation in it. But if you want to, if I want to give the introduction to subject more rigorously, maybe I should start with the very basic case where the target is a smooth projective variety. So beta is a curve class, and this moduli space of stable maps is kind of parameterizing maps from a curve which has at most nodal singularity and some markings on it, this P1 to Pn, and we expect the push forward of the class of the C to be beta. And the stability condition is these maps having finite automorphism. And on this moduli space, if you take a map and if you look at the cotangent space of the C at the mark point, at ith mark point, they patch together nicely and they form a nice line bundle. And if you take the first shown class of line bundle, you define these descendant classes. And the Gromov-Witten invariance for a given number, given n many cohomology classes is defined by this intersection number or this integral. So these are virtual intersection numbers. I'm saying virtual because we are not integrating over the fundamental class, but something called virtual fundamental class. And these invariants, they, for example, when m sub I is 0, this invariance count the class beta curves of genus G passing through the Poincare-duals of the cohomology classes that we described here.
Sorry to interrupt. Someone raised a hand. So, Sung Tang, do you have any question?
Okay, if not, let me move forward. Yeah. So Gromov-Witten theory. So this somehow like has many different properties and so on, and they are mostly the subject is mostly inspired from the string theory, and physicists somehow conjectured this mirror symmetry, and later it is proved by different people for different targets. But basically, genus zero mirror symmetry says like counting rational curves on a Calabi threefold is equivalent to studying the variation of hot structures on another Calabi threefold. And the counting curve side is called A model, and the hot structure part is called B model. But rational curves are genus zero, but Gromov-Witten theory can be defined for every genera, just we have talked a couple minutes back. And but the B side is kind of more mysterious. There are like some different theories that is described by physicists or mathematicians, and they want to settle down this part. And the first one of the first propositions for a higher genus part for B model came from this physicist, and the proposition they made for this higher genus B model theory is now known as BCOV theory, and there's this holomorphic anomaly equations in this BCOV theory, and it is kind of central to the subject. And that basically says, like, if you look at in their paper, these equations appear, and if you look at the second equation, you take this anti-holomorphic derivative of a function that is depending on G, and on the right hand side you can see that the Fg depends on Fg minus 1 and lower subscripts. So basically it is saying that the genus G information can be somehow related to the lower genera by some partial differential equation. And since we are taking anti-holomorphic derivative on the other side, and we have non-zero something on the other side, this is kind of called holomorphic anomaly equations. So physicists proposed this in the beginning of 90s, but the progress has been very slow. For example, at 2009, there's the work of Zinger for genus 1. And after almost a decade later, Ruan did some work on genus 2. But when it comes to 2018, there was some blast of progress, and Lo and Pandey proved this holomorphic anomaly equations for 3 different target spaces. For local P2, which is the canonical bundle of P2, some Calabi geometrical formal quintic, and this orbifold C3 mod Z3. And at the same time, Ruan, they proved holomorphic anomaly equation for every genera for the quintic as well. But so far, all these things are Calabi threefold geometries as predicted by BCOV theory. As mathematicians, we can ask, like, if there is this type of recursive relations among some FGs. I will ascribe, I won't describe what FG exactly is in the B model theory, but we will have an FG on the A side, and it is generating function of the Gromov-Witten invariance. And one can ask if such recursive relations, depending on the genera through partial differentiation, appears in different geometries or in different dimensions. So Pixton and Oberdig, among many things in their work, they proved holomorphic anomaly equations for elliptic curves and K3 surfaces. This is one-dimensional and two-dimensional instance, and this is not something physicists predicted. And Low generalized this KP2 example to KP3. So this is first higher dimensional example. And then Oberdig conjectured these holomorphic anomaly equations for Hilbert scheme of points on K3 surfaces. And he proved one holomorphic equation for every n. So basically, he showed instances of holomorphic anomaly at every even dimension. So Hilbert schemes of points on a surface, they are two n dimensional. So he obtained some even dimensional examples. And his conjecture is only done for genus 0 3-point invariance, proved for genus 0 3 invariance in his paper. So let me talk about our setup, and let's move on. So Z sub nx on Cn with this 1-1 action. So basically rotating each coordinate the same amount and gluing those points. And this action commutes with the diagonal action of the torus with these weights and induces an action on the quotient. So this way we see that Cn mod Z sub n is a toric Deligne-Mumford stack, and the main object that we are working with is the Gromov-Witten potential, which is a generating function for the Gromov-Witten invariance of this target. So, and we are considering, since this is a non-compact target, the very primitive Gromov-Witten invariance that I described is not applicable to this setting, because they were for a projective variety. Here we have a torus section, and we use Atiyah plot localization in some sense here to define the invariance, and the T-equivalent orbifold cohomology has this canonical additive basis, and the Gromov-Witten potential for this target is defined with this formula. This is basically a generating function for the Gromov-Witten invariance of this target. And we consider this potential after the following specialization of the equilibrium parameters. So these are either roots of unity or roots of -1, depending on the parity of the dimension of the target. So these are our main objects to study. So the first thing that we proved that this potential actually lies in a polynomial ring. And after that, this is the main result of our first paper. After that, we proved this recursive, we define these systems of partial differential equations depending on the genus recursively. So basically, we obtained holomorphic anomaly equation for every odd n in this way, and for every genera greater than or equal to 2. And we also proved the similar thing for even dimension when n is greater than or equal to 4. So basically, we obtain instances of holomorphic anomaly equations at every dimension and for every genera greater than or equal to 2. So these are the first holomorphic anomaly equations at every dimension and arbitrary genera greater than or equal to 2. So this is the first result. This is the main result of the first paper. So for the second paper, the main target we are working on is actually Kpn-1, which is the canonical bundle of which is the canonical bundle of the projective space, or total space of the canonical bundle of the projective space. So torus has this standard action on projective space, and this has a canonical lift to the canonical bundle. Again, we can consider the torus equivalent Gromov-Witten theory of this target here. So, and the T-equivalent cohomology has this additive basis again. This time we have this H. It is because it is coming from the equivalent first Chern class of the tautological bundle of the projective space. So we consider again the Gromov-Witten potential associated to this target, and it is given by this generating series. So it is again a generating series for Gromov-Witten invariance of this Kpn-1, and we consider this invariance after again a specialization of equivalent parameters. So this is our setup for the second paper, and what we proved is a crepant resolution conjecture. Let me briefly tell what it is. So if you blow up this unique singular point of this of the variety Cn mod Zn, you obtain the Kpn-1, and this is known to be a crepant resolution. It means kind of, in some sense, naively saying there is some graded vector space isomorphism between the cohomologies that I described. And under this graded isomorphism, one expects the Gromov-Witten invariance or Gromov-Witten theories of both targets match. So the crepant resolution predicts that the Gromov-Witten theory of Cn mod Zn and Kpn-1 are equivalent in some sense. And in the main result of the second paper, we again showed a polynomiality result. We showed that this also lies in a polynomial ring. And then we had another polynomial ring for Cn mod Zn. We established a ring isomorphism between these two rings, and we showed that ring isomorphism, it is epsilon here, is sending one potential to the other after some rescaling, and the rho is some root of -1 here. So this is the second result. Basically, we showed that the Gromov-Witten theories of both targets are the same in some sense. So before this, people did a lot of work on when n equal to 3, so local P2 and C3 mod Z3, with different approaches, the approach we take here for arbitrary n is kind of generalization of what Lo and Pandey did for C3 mod Z3. So this is the main result of the second paper, and I will try to elaborate this result in the rest of the talk. Do you have any questions so far? Okay, so if no questions, let me go further. So it's written here MGM bar, but I think the bar is not shown in the title somehow. But anyway, so probably most of you know that the stable graphs and MGM bar have like strong connections because the points of MGM bar are stable curves. And if you take a curve and if you take its dual graph, you can have its dual graph. And it is for the MGM bar, this dual graph has some more decoration, and it is called stable graph. So it has vertex set, edge set, leg set, and for every vertex we have this genus assignment, and at each vertex we have this stability condition, which is coming from the stability condition of the moduli space of MGM bar. And for every graph gamma, you can describe a canonical isomorphism, canonical morphism, whose image is equal to the boundary stratum of the stable graph gamma. So these stable graphs, basically, they kind of parameterize the boundary stratum of strata of the MGM bar, and this is the morphism that is kind of describing that. I will use this later. That's why I need to introduce this one. So let me go. So there are these maps between these MGNs or MGMs. Since I used small n for my target, I didn't want it to be confused with here, but I already wrote n anyway. So yeah, so we have these maps among these MGNs, and one map is this gluing map. It is gluing the last two marks. So it increases somehow genus by 1 and reduces the mark points by 2. And there's also forgetful map. You can forget the last mark, for example. And if the curve is not stable, you can stabilize it in some sense. And there's also another gluing map, which kind of glues two curves to each other by replacing the last marks with a node. So you glue them along those two last marks, and you get this map. I needed to introduce these things because I will define a cohFT, and which is cohomological field theory. And the idea of cohomological field theory comes from Gromov Witten invariance. Manin and Kontosevich, they introduced this axiomatic approach to Gromov Witten invariance. And then those axioms, if you take them somehow, you can define some more general theory. And if some other invariants satisfy similar properties, you can analyze them through the theory of through these cohomological field theories. So basically, Gromov-Witten theory gives you a cohomological field theory, but cohomological field theory is now much more general concept than the Gromov-Witten theory. So let me introduce the basic setup of cohomological field theories. So here, in the basic setup, we have a vector space, which is finite dimensional, and a symmetric non-degenerate bilinear form. And sometimes we have also this element, which we show 1 because it's going to be unit of the cohFT. So what is a cohFT? So cohFT is a system of tensors, which are SN equivariant, and they satisfy some compatibility properties under the maps that we introduced here, PQR. So what are those properties? I will show them, but I don't expect anyone to like grasp them fully. So these are the properties, these are the axioms. So pullback by these maps are kind of related to relates the elements of this system of tensors. For example, first two basically says like if you pull back by Q and R, it is related to the other elements by a contraction of the non-degenerate form here. And if the first two condition is satisfied, we call this system a cohFT. And if the third line is satisfied, we call this system a cohFT with unit. And 1 is the unit of the cohFT here. One can define a product on the vector space by the non-degeneracy of the eta, so the form, in this way. And if the cohFT is has a semi-simple basis, if this vector space has a semi-simple basis or an idempotent basis, then we call the cohFT semi-simple. But in the Gromov-Witten theory, the base thing is not a vector space; it is a module over a ring. So this setup also applies modules over some certain ground rings. So in this case, we picked it's as a Q, but it doesn't have to be Q. So for the Gromov-Witten invariance, for example, it is the base ring is Novikov ring. And if you have a cohFT, there are some actions that you can apply to your cohFT to produce new cohFTs. One of them is this translation action. If you have a formal power series whose coefficients are vectors in this V, then you can produce a new cohFT out of omega. So it's called translation by T. And also, if you have some matrix series which satisfies this symplectic condition, then you can also produce new cohFTs out of a cohFT by another action. Let's call it R action. And this R action is kind of given over the stable graphs. So for every Gn, there is finitely many stable graphs, and for each stable graph, you define somehow what should be the contribution, and you sum them up over the stable graphs. So for vertex contribution, you have something coming from omega, and for edge contribution, you have something from this R matrix and omega, and for leg contributions, you also have something from coming from R matrix and omega. And you patch these things together and push forward to the MGM bar, and you get your R omega cohFT out of omega. So basically, we have two actions. Let me summarize these things. Maybe not here. Let's introduce something else first. So if you have a cohFT, then you can define its topological part, and topological part of a cohFT is basically restriction to the cohomology degree 0 of the main cohFT. And topological part of a cohFT is a cohFT as well. And if your cohFT is topological, then you can obtain it from the 0-3 part using the cohFT axioms. So topological field theories are kind of much nicer than the general cohomological field theories. And Givan-Telemann classification says if you have a semi-simple cohFT with unit, then there exists a unique R matrix where you can reconstruct your big omega from its topological part by two actions. So one translation action and one R action, both described by the R matrix here. You obtain first your T series and apply translation action, and you apply R action with R matrix, and you get your omega back. So this is called Givan-Telemann classification for the semi-simple cohFTs. Let me summarize this result. So you have your cohFT omega, you restrict to the degree 0 part, you get the topological field theory of the cohFT. And this is equivalent to knowing that 0-3 part of the topological part. But the 0-3 part is also equivalent to something called quantum product that we described a couple slides back. And if you want to go back, you need to find this unique R matrix. But finding it is kind of challenging but we know that around the semi-simple point, this R matrix satisfies the differential equation. I know this is called flatness equation. But the solution of this flatness equation doesn't give you fully the R matrix. It gives the R matrix with an ambiguity, and if you want to fix that ambiguity, you need some other things. But at least it tells you something about this equation tells you something about the R matrix. If you want to fix the ambiguity, you need to either have a conformal co-HFT or you need to do some other stuff if you don't have a conformal co-HFT. So, but if you want to prove something structural about your big omega, your main co-HFT, then you need to first know your quantum product so you can know your topological part, and you need to know as much as you can about this R matrix so you can prove something meaningful about the main co-HFT. Any questions so far? Okay, so if you want to show that two semi-simple co-HFTs are equivalent, then the thing you need to show that their quantum product and R matrices are equivalent in some sense. So this is also one technique that we will use later. So quantum product R matrix, they describe the semi-simple co-HFTs. So let me talk about a little bit the genus zero theory of Cn mod Zn. So there is this J function and I function. If you attended some Gromov-Witten theory talks, you probably heard these things. So J function encodes the genus zero Gromov-Witten invariance, and the I function its origin is coming from the Hoche theory part, and this is about the count. It kind of encodes the count of periods here, but and if you want to find your I function somehow, there are like different methods out there, and for this target we use the Corti, Irtani, and Tseng's work, and we find our I function for this target. And what is the use here? So control of Gromov-Witten invariance, understanding of or Gromov-Witten invariance could be hard, but this type of I functions are kind of better to manage in some sense. And again, by the work of Corti, Irtani, and Tseng, we proved this mirror theorem. Basically, we said like this J function is actually this I function after a change of variable. And now we can work the J function through I function. So this I function satisfies the following the differential equation, and this L series, this formal power series L or function L appears naturally in the differential equation, and the way to prove such a mirror theorem kind of requires understanding of something called Giventel's Lagrangian cone. So Giventel gave this formalism of genus zero theory through a symplectic vector space and a Lagrangian in it. And this Lagrangian has some strong properties. And there is some process called Birkhoff factorization, and you use the properties of this Lagrangian cone. And in this Lagrangian cone, if in this process, Birkhoff factorization process, this fractal L sub I operators appear, and basically they are somehow there are some series Ci appearing as a rescaling in front of this D operator. If you want to define this operators in our geometric setup, so this Ci series are important in some sense in this Birkhoff factorization. So And if we are talking about a factorization, then we kind of apply these operators back to back. Then product of this series are also important. So you take the product of C0 to CL in some sense, and we define this to be KL. And we managed to obtain our quantum product with this nice formula. If you take your phi I and if you take your phi j, if you take the quantum product, then you get this formula, this nice compact formula. How do we prove such a thing? We use somehow Giventhal Lagrangian comb to prove first the generation argument. And then there's this work of Zagier and Zinger for some hypergeometric series and their Picard-Fuchs equation. And using their methods, adapting their methods, we obtain some relations between this C series and K series. For example, first one is periodicity, the third one is somehow symmetry, and so on. And combining with this generation argument, we can write our quantum product with this compact formula. So now we have our quantum product, and now we need to find our R matrix to be able to say something. But if we can't find R matrix, at least we should understand R matrix as much as we can, so we can say something about, again, our Gromov-Witten QHFT or Gromov-Witten potentials. So then to find the to kind of say something about the R matrix, we need to go to this flatness equation. And in flatness equation, we do some change of variables to kind of make our formulas to kind of make our flatness equation look like in a manageable form. And these are like new series that we introduced, and we do some change of variables in this setting, and then our flatness equations looks like this. So instead of R matrix, now let's call this modified R matrix. This P matrices are entries, IJ entries of the modified R matrix. So yeah.
So when you say change of variables, do you mean are you changing variables in Z, or are you applying a gauge transformation? Can you say a little bit more about what you're doing?
This is exactly what generalization of what Pandey and Low did their paper. There are both of them. You apply the first coordinate change matrix, and also you change your Z, you rescale your Z. So you do both of them. So, and then your flatness equation takes this form. And this ION is an involution. It's just an involution of the discrete set of numbers from 0 to n. It replaces 0 and n and keeps the others same. But did I answer your question?
Yes, thanks.
Okay. So this is how our equation looks like. And for example, for n equal to 6, this is how it looks. And now let's go forward. So let's define this wild ring. So you have this A1 to AN minus 1. In this case, it is A1 to A5. And take all the higher order derivatives with respect to this operator D. Okay? Differentials with respect to this operator D. And put them in a ring. And using the methods of Zagier and Zinger, we can show that the P0J part lies in CL, so it lies in this basic ring. And if you look at the formulas, you can see that the P0J is in CL, and you keep taking derivatives and putting these A1s, A2s, A3s is there. That means each Pij lies in this differential ring, okay? So, and then this differential link, for example, has this 5 rows of generator for n equal to 6 example. I will give this n equal to 6 example most of the time to kind of better give the idea of the general thing. So, but this is not manageable if you want to say something about the Pijs, because this is some very big thing. you need to do some simplifications. So there are a couple of simplifications we do, 3 simplifications mainly. The first one is saying that actually this differential ring has finitely many generators. It puts a bound on the orders of derivatives of the generators. And the second simplification is kind of some symmetry relations. For example, if you look at the bullet point 1, for n equal to 6, for example, a1 is same as minus a5. So you don't need a5 then, and so on. And there's a third simplification. It says like after the symmetry cancellations, one of the first derivatives of some elements can be described in terms of the first derivatives of the other elements and their squares and some polynomials in L. So let me visualize this. So this is our differential ring for n equal to 6. First simplification basically reduces this number of generators to here. We have this ladder type of remaining generators. Second simplification is symmetry relations, as I just described. And for example, I told for n equal to 6, a1 is same as minus a5, a2 is same as minus a4, and a3 is 0 in this case. So this is what we have left. And dA2 here, dA2 can be described by a1, a2, and derivatives of a1. So we don't need dA2 and d square a2, for example, in the example of n equal to 6 case. And we have this for every n, and we have this remaining set which we showed with factor s sub n, and there's the single element at the very bottom each time. For example, for n equal to 6 it is a2, for n equal to 10 it is 4, for n equal to 20 it is 9, a9, and so on. So the number of remaining generators gets larger and larger as n goes to a higher thing, but every time we have the single element at the very bottom. And our holomorphic anomaly equations are described partial derivative with respect to this very bottom thing. So so basically, after this simplification, we say that this differential ring is the quotient ring of the free ring described by the whatever the things we have here after the simplifications. And since Pij is in the differential ring, they should have a lift. They have lifts to the free algebra, but there's a canonical one. So we know that, for example, let's go with this example. P0j lies in CL, and if you take derivatives, that means P5 lies in here. And we first time introduced this A1 here, and that means P4 lies in here. And we took one derivative, then we have the A1, but we introduced A2 here. So this part should lie in here. But if you remember, the A2 can be described by A1 and A2 and derivatives of A1. When we pass the next step, we don't have the A2, we still have A2. And the next step, the last step is this. So we start from top and we go from bottom. And we know that the P0j lies in CL. And we lift the rest of these elements one by one to the very last ring we have here. And this can be done in for every n. So this is how we lift to the free algebra. And if you go back, now I told you that for n equal to 6, we are going to take derivatives with respect to a2. Let's see what's going on. So P0 doesn't have any A2, so its derivative with respect to A2 is 0. P5 doesn't have any A2, its derivative is 0. P4 doesn't have any A2, its derivative is 0. But P3 doesn't have a 0 derivative, and it is what is derivative here is P4j to the k minus 1 here. And the question, what happens to the next elements then? It turns out that P2 doesn't have a 0 derivative, but because of the relations, it turns out that P1 has 0 derivative with respect to A2. And this is not a coincidence, this is a general phenomenon. For example, for odd case, if you take derivative with respect to the very last element that we have, there is only one non-zero derivative. And for the even, we have two non-zero derivatives. So these are going to be important in the proof of holomorphic anomaly equations. So what did we do? We obtained our quantum product, and we kind of proved something structural about our our modified R matrix or P matrix here. So now we know something about the P matrix, and the question, can we use this and prove something? And yes, we can. So by the given Telemann classification, you can write this potential as a sum over the graphs, and if you apply the given Telemann classification, then you see that each contribution is product of vertex, edge, and leg contributions, and the vertex contribution is given by this wild-looking formula, but the only thing we need to understand here is the following. Vertex contribution is just a polynomial in P0j to the k. And we know that P0j's are polynomials in L, hence this is a polynomial in L. And if you look at the edge contribution, then edge contribution, so this zeta is a complex number. It is just primitive root of unity. It is not important. Just focus on this products of two P's here. So Pij's are we have the lift to the free algebra that we taught, then their product has a lift to there, right? So that means this edge contribution lies there. But when it comes to leg contribution, we have a single P, but these K's are in front, and K's were products of C's. But we don't know if C's are algebraically independent with A's, so we need to throw some more elements to make sure that nothing weird is going on. So then we obtain the lift of vertex, edge, and leg contributions to the very last ring here, last free ring here, and we define this to be f sub c n to the zn, and this is where our potential lifts to. So this is basically saying that the Gromov-Witten potential is a polynomial in this free algebra. Any questions so far? So this is our polynomial to result. Okay, if no questions, let me move forward. So if you look at here, you see that vertex contribution lies in CL. That means derivative with respect to any A is 0 for a vertex contribution. And so we have this vanishing result. The reason I wrote here floor function of n-1/2, that is the index of the very last element of after the simplifications. So for odd and even case. And for odd, if you remember, we had this lemmas, right? So derivative with respect to this a sub floor function of n-1/2 is given by this formula for odd case and given by the other formula for even case. And if you go back to here to edge contribution, for example, if you take the derivative of these things, since the derivatives of this p's with respect to a sub s is 0 in general, you obtain the following thing. This two lemmas implies these two things. If you take contribution of edges, and if you take the derivative with respect to as, you just have product of two p's or two products of two p's, and depending on the parity. And but if you go a little bit back again, so this is leg contribution. Leg contributions has only one p and some scaling in front of them. So then that means taking derivative with respect to as of an edge contribution produces you product of somehow two leg contributions in some sense. And this is the heart of the proof of the holomorphic anomaly. So if you don't have any insertions, if your m is 0, if you're just like considering fg's here, there is no legs, because legs correspond to mark points in a stable graph, and edges correspond to nodes, and vertices kind of correspond to the irreducible components. And since we don't have any legs in the we don't have any insertions, that means in our source curves we don't have any mark points, and we don't have any legs here, so we only have vertices and edges. And if you take the derivative of this one with respect to AS, we just said like this vanishing result, vertex contributions derivative with respect to A sub S is 0. So this derivative doesn't see that and only take the derivative of the edge contribution part. And we get the second line. But we just discussed that derivative with respect to AS for an edge contribution produces you leg contribution somehow. So taking derivative with respect to AS then becomes equivalent to breaking an edge into two legs. So if you have a stable graph and if you break an edge into two legs, there are two possibilities. Either your graph stays connected and you have two legs, or your graph becomes disconnected and decomposes into two graphs, each having one leg. Okay, so these are the possibilities. And somehow, if we take our gamma and if we have a connected graph after breaking an edge E tilde, it corresponds to another contribution for another potential with two insertions, this phi s, and it becomes, if the graph is disconnected, it becomes the product of two different contributions in different FGs. And this is how we get our formula. So on the right hand side, you kind of break an edge and you turn it either into one less genera with two legs, or some G1 and G2 where their sum is equal to G, with each having one leg. So you sum over all possibilities and you mesh these potentials in this way. This is how we proved it. Any question? And for even case, we have a similar proof. Let me pass to the crepant resolution part. So this I function of Kpn minus 1 is known for a long time. And the mirror theorem we have also mirror theorem here. We have again Birkhoff factorization. So in the second paper, we kind of want to show that these two theories are equivalent. Then we need to show that everything applies to the other one has to apply here. So we go over the similar process. And in this process, we define this L series and C series, K series, and AI series. All this analogous things has been done on this part as well. And it turns out that the quantum product is given by this formula. Hi and Hj, when you take the quantum product, it becomes this formula. And this really looks like the same if you go back and look at the quantum product for phi i's and phi j's. But of course, the series there, they are centered around some variable x. And here, the series are centered around some q. And one has to relate this x and q in some sense to kind of match the two theories. And hence, we can kind of relate this C series and K series. And flatness equation is exactly of the same form, but you may say that like then if the equations are the same, if the products are looking the same, then you are done, but not, we are not done because the initial conditions are not the same. One has to work with the initial conditions to match these things. And the change of variable that we need to do here is q equal to x to the minus n. There are some geometric motivation behind that, but if you can forget about the geometric motivation and you can try to start matching this L series because you have their formula. You have their formula in your hand, And if you want to directly somehow relate this else, you can try something. For example, you can take n power of both of them and you can try to relate each other. And that also gives you this relation. And under this identification, these L series are related to each other via this identification. Here, rho is a root of -1. And the D operators are related to each other with this way. So this kind of takes one Picard-Fuchs equation to the other if you do this change of variable. And also you need to change your Z with rho Z to do that. So that means at the level of Picard-Fuchs equation, things are matching analytically in some sense. And if you use that idea and if you match the initial conditions using the orbifold quantum Riemann-Roch theorems of Tseng and quantum Riemann-Roch theorem of Tseng-Giventhal, and if you use the matching of the Picard-Fuchs equation, you can show that these two things match. The initial conditions are matched using some asymptotics of oscillatory integrals coming from lambda Gisburg mirror of the Kpn -1. You give the asymptotic expansion two ways, and that gives you the matching. So this part is kind of much more technical. But you have the matching of these things, then you may try to match the rest, because this is just the first row of the modified R matrix. It is not all of the R matrix. And we couldn't we didn't match the rest analytically. We matched the rest formally. So if you remember, the lifting procedure starts with P0J. If we manage to match P0Js, the lifting procedures are similar. And if you can match the lifting procedures in a formal way, then you can match the modified R matrices. So we matched our under these identifications, we matched our quantum product and we matched our R matrices, but there is this row in the front of Z variable. So it is not clear if the co-HFTs are going to match or potentials are going to match at the end. So you need to do a little bit of more work. So these identifications, they define a ring isomorphism between these two rings where we lift our P matrices or modified R matrices. And again, if you apply the Giventhal-Telemann classification, you get a similar result here. So you have the lifting of the potential to this one, and this row scaling Z variable, it cancels out nicely if you keep track of after this ring isomorphism. If you keep track of the relations between vertex contributions and edge contribution and lex contributions in both potentials, you see that things are canceling each other nicely, and this row comes in front of the potential after the matching, and you match the potentials with this way. So this is morely a formal matching, because we didn't match all of the R matrices analytically. So that's the end of my talk, and I want to thank you. And if you have any questions, I will be glad to answer your questions.